We have now approached the last unit of this course, which is the unit on the circuits aspects of all the devices that you have looked at so far. Okay. So, if we let us just summarize our journey. Okay. We started off with some ideas on quantum mechanics, and we looked at some interesting properties like the wave particle, the wave function, etc. And we used those ideas to develop concepts on how carriers would behave in a solid. So, electrons in a solid. So, and we looked at the formation of the band gap, what the valence band is, what the conduction band is, very briefly. And we use those ideas to then develop a solid structure for device physics. Okay. And here we studied the basic properties of semiconductors. We looked at the formation of junctions, and we looked at some of the devices, particularly the metal semiconductor junction, the PN junction, and in transistors we particularly paid attention to the BJT and the MOSFET. And here we developed a huge set of tools, okay, such as the Poisson's equation, to study the behavior of all these devices. And throughout the study, we always try to finish or wrap up every device or every concept with the impact on circuits, right. We looked at the small signal models of many of these devices, and we now are ready to make use of all this knowledge to see the circuit implications. Okay. And what we will be doing in this unit is essentially focusing on the MOSFET. We will not use any other device, okay, because circuit design, circuit theory or analog circuits is an entire course in itself, and we are not here to completely explore every detail of analog circuits, although this is a course that I do teach at the graduate level, but at the senior undergrad level, but this is not the place for a exhaustive course on analog circuits. But instead the point here is to introduce all of you to circuits, okay, introduce all of you to so that all of you at least get a flavor of what circuit design is all about, okay. And most importantly, try to see how different circuit parameters, okay, the circuit level parameters, how the circuit level parameters are connected to device physics, which in turn is connected to the behavior of electrons in a solid. So, every time we introduce a parameter, we will try to hunt our way back to some elementary concepts. Okay. So, we will focus on the MOSFET and we will explore some very basic circuits, particularly the use of the MOSFET as a switch and small signal analysis with the MOSFET, and using the MOSFET to build an amplifier. And we will only look at a single stage amplifier, and particularly something that gives you gain, which is something called as a common source amplifier. Okay. And of course, once you understand the methods of using these techniques of small signal analysis for amplifiers, you can extend those techniques to other circuits. And finally, we will look at two important properties, very quickly the frequency response of MOSFETs, and secondly the noise in MOSFETs, and with that we will complete this course. So, I hope all of you find this last unit to be useful, because it completes the arc. So what we did is we briefly looked at many topics. So, this course is more wide than deep. It looked at many topics from quantum mechanics to solid state physics through device physics and engineering, and finally it is going to terminate with the understanding of circuits. So, let us start off by looking at the MOSFET as a switch. Again, we are going to go back to our traditional example that we used to introduce transistors, which is I have point A and point B, and I want to send a message from point A to point B, and I need a switch in place. So, when the switch is closed, the message here gets to point B, and when the switch is open, nothing happens at point B. Okay. So, here is a more complete circuit. Now, let us say we want to use the MOSFET as a switch, okay, a simple switch, and this kind of a circuit is extremely useful for memories, for example, where you have a MOSFET as a switch and a capacitor, and you write information on the capacitor and you open the switch and the information is retained on the capacitor. So, this is it is a form of memory. Okay. The other applications are your circuits and displays or any active matrix systems, wherein you have a MOSFET and you have a capacitor again, and you store and then you have a light emitting material. So, for example, say an LCD, and you store information on this capacitor and you open this MOSFET and you have the voltage here driving the LCD, so that you can see the color, the different levels of brightness on your display screen. So, this the use of a MOSFET as a switch is extremely important, even when it comes to analog circuit applications. And more than that, the use of a MOSFET as a switch is the essence of digital circuit applications. Okay. So, let us study some of the important aspects of the MOSFET working as a switch. So, for a transistor could replace the switch, because you need a control signal and you need these two terminals. So, we have looked at BJTs, but we are not worried about BJTs in this section of the course, and instead we will focus on using the MOSFET. All right. So, the first question, okay, if I were to use the MOSFET as a switch, okay, and I want low small signal resistance across the switch, do I bias the MOSFET in linear mode of operation or saturation mode of operation? That is the first question. So, just to recollect, what is the linear and what is the saturation mode of operation? So, you have your current, your output characteristics of the MOSFET. You have IDS versus VDS, okay, and let us say it looks like that. And we know that when for some particular VG, we know that when VDS is greater than or equal to VGS minus VT, the MOSFET is in saturation mode of operation, and when VDS is less than VGS minus VT, we say that the MOSFET is in linear mode of operation. Now, what is the property of an ideal switch? The ideal switch should have a low resistance when it is turned on or when the switch is closed. So, this is the resistance of the switch, okay. So, this is RDS, let us say, and that is, it is desirable that this resistance be low, okay. And now the question we are asking is, do we bias it in linear or saturation mode operation when for having a low small signal resistance, So, what do you mean by small signal resistance? It is dVDS by dIDS. That is, you have fixed the drain voltage at some DC point, and we are having some current in response to that drain voltage. Now, if we fluctuate the drain voltage around this point, that is, we have a small signal which we will represent with a small VDS. If we have a small fluctuation here, how does the current fluctuate? By how much does the current fluctuate? So, that is what you mean by small signal analysis. Now, where is the small signal resistance lower, in saturation or in linear? So, if you were to demarcate the saturation region and then you draw the linear region here, what is the small signal slope in the linear region? So, we have set a VDS and now we are going to fluctuate a small signal VDS around this, and we are going to see a fluctuation in the current in response to that. So, this slope is essentially the resistor. So, as we move the current voltage up and down, the current moves up and down. Okay, so, the current changes by that level, and therefore, the resistance here is some values which we will call as R linear, which is your dVDS by dIDS. Now, what about in saturation mode? If the MOSFET has got ideal characteristics and this is perfect saturation, that is, there is no channel length modulation, a large fluctuation in the voltage does not fluctuate the current too much. That is, even if dVDS is very large, your dIDS is almost 0. And what is dVDS by dIDS in saturation? It is going to be infinite. Okay. Therefore, the resistance, the small signal resistance for a MOSFET in saturation is infinite, and this resistance is something called as the output resistance of the MOSFET. Okay. Whether it is a linear or saturation, this resistance between source and drain that we are talking about is something called as the output resistance of the MOSFET. So, RO for a MOSFET in linear is finite, it is small, and RO for a MOSFET in saturation is infinite. Therefore, it is definitely preferable to bias the MOSFET in linear mode of operation if you are using it as a switch. So, which means that if I am going to have to send data from point A to point B and I have a control. So, let us say point B is at our reference. So, let us say that is the source, and we have a control signal which is the gate to source voltage. So, the DC, it has got a certain DC level here. Okay, and we have the the gate to source voltage, and we have a drain to source voltage. So, let us say that with time the information being sent at point A has got a certain DC value. So, that is your VDS, and on top of that we have a small signal information that is being sent to B. So, it is this information that we want appearing at point B. So, what is needed is that this DC level, okay, so this fluctuation is very small. So, that is not going to be very large. So, this DC level is expected to be smaller than VGS minus VT. So, in that case the MOSFET will be in linear, but if this DC level is increased and if this DC level is going to be larger than VGS minus VT, then we have the MOSFET in saturation. So, here is a simulation. Okay. So, the answer to this question is we want the MOSFET in linear, and to prove the point, here is a simulation which is done using AIM-SPICE, which is a software. Okay. And the simulator takes into account this circuit. So, we are simulating this circuit here, shown here. So, the MOSFET we are considering has got a channel width of 100 micron, channel length of 10 micron, threshold voltage of 2 volts, a mobility that is very low, and we will so basically this is a thin film transistor MOSFET which has got disordered semiconductors, a COX which is 9.73 E minus 8 farad per centimeter square, and we have point B here which has got this this terminal circuit. Okay. So, naturally if the MOSFET is open, point B is pulled to ground, it is kept at ground because of charge draining off through this resistor. Now, what happens? So, let us say we bias the MOSFET in linear mode. How do we know that So, this diagram corresponds to linear mode. How do we know that this is linear mode? This signal that you see here, this square response is the gate of this MOSFET. Okay, it is the gate voltage of this MOSFET, and the gate voltage is going from 0, it climbs to 10 volts and stays at 10 volts for some time and comes back down to 0. So, that is the gate of the MOSFET. The source is generally at ground because that is my point B. So, this line you see here is point B, and this is the voltage fluctuation at point A. So, you can see a small signal that is trying to get across. Okay, it is a dying out sine wave, but what is the average value of the signal? What is the DC value of the signal? The DC value of the signal is around this point, so which is about 2 volts. And what is the DC value of VGS? That is about 10 volts, and the threshold voltage is 2 volts. So, definitely VDS is less than VGS minus VT, which means that the MOSFET is in linear mode operation. So, when it is in linear mode operation, let us look at what happens at point B. Okay. So, point B is seeing a signal like this. When the MOSFET is got 0 gate to source voltage, the MOSFET, the switch is open. So, point B sees nothing because you have A that is fluctuating and then the circuit is open, and B that is connected to ground with the 500 kilo ohm resistor. Okay, so, point B sees none of this fluctuation, which is what is expected. But the moment the MOSFET turns on, you can see point B climbing up and almost following point A, except for a small delay. It is almost following point A, and the moment the switch closes again, point B loses connection with point A and it goes back to 0. So, you can see that the signal from A is successfully transferred to B if you keep the MOSFET in linear mode of operation. Now, what about keeping the MOSFET in saturation mode of operation? Okay. Now, this is the case where the MOSFET is in saturation mode. How do we know it is in saturation mode? So, the gate voltage is still the same. When it is on, it is still 10 volts. But let us look at the voltage at point A. Okay. The voltage at point A is this is 500 kilo ohm, that is point B, and this is point A. This is where the signal is coming in. So, that is 10 volts, that is VGS. What is VDS? So, point A has got a signal that looks like this, right, and what is the DC value of that signal? That is somewhere here, and that is about 9 volts. Okay. So, VDS is about 9 volts, VGS is about 10 volts, and what is VGS minus VT? It is about 8 volts. Therefore, VDS is greater than VGS minus VT, which means the MOSFET is in saturation. So, now let us look at what happens to point B. Is it able to capture the signal? So, this is point B. You can see that once the MOSFET is turned on, its voltage increases, but it is not able to so clearly track the message coming in from point A. You can see there is some very light movements, but generally it is a constant, and then it dies out. Okay. So, point B in this case is not able to track the signal from point A because the MOSFET is in saturation and it has got a very high output impedance. Okay. So, this is a very illustrative example where you say that we need the MOSFET to be in linear mode operation, and because it is going to have a low output impedance in linear mode operation. So, this is the summary. So, in linear mode operation, the MOSFET has the small signal output impedance of the MOSFET is very low, and in saturation mode operation, the small signal output impedance of the MOSFET is very high. Okay. And therefore, we want the MOSFET biased in linear mode operation for use as a switch. Okay. So, we have decided it is a linear mode operation. Now, what is the resistance of the switch? Okay. So, what do you mean by the resistance? What is the resistance of the MOSFET switch? So, do forgive this plot having all these scripts, because this is a image that is transferred from a Mac to a PC, and it generally happens to have these kind of errors. So, what we are trying to show here is the output characteristics, it is VDS versus IDS, the rest of the details are not important. Okay. So, the point of this is, okay, in the previous slide we realized that we should bias the MOSFET in linear. Okay. Now, the question is, what is the value of the resistance? What is the output resistance of the MOSFET? So, we are talking about the small signal resistance of the MOSFET. We are not talking about a resistance measured as VDS by IDS, no, because if it is VDS by IDS, even the saturation mode, in the saturation mode the MOSFET does have a finite resistance, right. You have, let us say, a VDS of 5 volts, and let us say the VGS is whatever 3 volts, and therefore, the MOSFET is in saturation, and let us say there is a current of 10 microamps. So, the MOSFET has got a VDS by IDS of 5 volts by 10 microamps. So, you could say that effectively that is the resistance of the MOSFET. No, but that is not what we are talking about, because that is the large signal behavior of the MOSFET, and that is a non-linear behavior. So, it is really not appropriate to define a resistance there. What we are interested in is the small signal resistance. Okay. So, I am reiterating this point, small signal resistance of the MOSFET, which is for a small fluctuation after you have set all the DC voltages. You set all the DC voltages, source is at ground, the gate is at some voltage, so that with respect to ground you have a certain VGS, and the drain is at some voltage, and with respect to ground you have a certain VDS, and this VDS is less than VGS minus VT. So, this is smaller than that, and now on top of that you have a little fluctuation, and therefore, you have a little current that is DC, and then you have a fluctuation in the current, and this fluctuation is defined by the small signal resistance of the MOSFET. So, that is the resistance we are after. So, what is the value of that? So, the value of that, since we have biased the MOSFET in linear mode operation, what is IDS? IDS is mu Cox W over L into VGS minus VT minus VDS by 2 into VDS. And if my VDS is much smaller than VGS minus VT, we could say that we are going to ignore this term, okay, and therefore, your IDS is approximately mu Cox W over L into VGS minus VT into VDS. Okay, so, this is something called as deep linear, I mean it is very linear operation. VDS is much smaller than VGS minus VT. So, now what is the small signal output impedance? What is the output impedance of the MOSFET? It is dVDS by dIDS, which is what? 1 by mu Cox W over L into VGS minus VT. This is nothing but the slope of the IDVG characteristics in the linear region. So, since it is deep linear, we are going to set the VDS to be very low, and we are talking about a slope in this region here. So, this slope is given by, that is inverse of that slope if you wish, because that is an IDS versus VDS characteristics. The inverse of the slope, which is dVDS by dIDS, is given by 1 by mu Cox W over L into VGS minus VT. So, this is the quantitative estimate of the small signal resistance of the MOSFET. Okay. So, here there should not be a VDS by 2 term existing. So, that part is probably not very accurate. Okay. It is a typo on that slide there. So, let us now play this game of connecting all these properties to our understanding of the device physics. Okay. So, let us see whether we can use this as a refresher for your device physics. Now, as a circuit designer, you have identified that this is the small signal output impedance of the MOSFET when it is in linear mode operation. So, firstly, does it make sense? When the mobility goes up, should the resistance increase or decrease? Since the mobility goes up, the carriers move faster, the current increases, therefore, the resistance should decrease. So, that makes a lot of sense. If Cox goes up, the field effect improves, the current increases and the resistance decreases, that also makes a lot of sense. If the MOSFET has got a large channel width over channel length, large aspect ratio, the resistance should definitely go down. So, that makes sense. And if the Vt is very small or Vgs minus Vt is very large, definitely you have larger inversion charge and you have a lower resistance. So, that also makes a lot of sense. But let us now go ahead and start defining each one of these terms. What is mobility? Because so we are talking about the output resistance of the MOSFET. Now, what is the mobility? The mobility is connected to the mean collision time, it is q t collision by the effective mass of the carrier. What is q? Q is your 1.6 into 10 power minus 19 coulombs. What is mean collision time? Mean collision time is the time for the is the mean time between the scattering events of the carrier that is scattering through the lattice and through the defects, etc., thereby giving you a definition of mu, which is your Vd is equal to mu times electric field. What is the effective mass? The effective mass is dependent on the shape of your Ek diagram. You have an energy, you have a momentum or the K space, and let us say you have your Ek diagram. So, let us say that is the conduction band edge. We saw that this the valley of this conduction band edge can be approximated as a parabola. Okay. And why can it be approximated as a parabola? Because your in a classical sense your energy is p square by 2m, and this p is nothing but the momentum, which is also h bar k. So, it is h bar k square by 2m, and this m is nothing but m star, where m star is the effective mass, and therefore, this is a coefficient attached to the k square dependence or a parabolic dependence. So, it is an approximation here. And what is the effective mass? We identified it from the second derivative of E. So, dE by dk is h square by m into k, and d square E by dk square is h bar square by m star, and therefore, your m star was nothing but h bar square by d square E by dk square. So, therefore, the shape of the Ek diagram is directly going to impact the output impedance of your MOSFET. So, that is your mu, right. What is Cox? Cox is nothing but the capacitance, the gate capacitance, the insulator capacitance per unit area of your capacitance voltage characteristics or your MOSFET, sorry, and that is nothing but epsilon ox by T ox. It depends on the thickness of the oxide. Aspect ratio is the geometry with which you have designed the MOSFET. VGS is the applied gate to source voltage, and what is VT? VT is the threshold voltage. It depends on the flat band voltage, it depends on the depletion charge divided by Cox, it depends on 2 phi f, the surface potential reaching 2 phi f. And what is VFB? VFB is the flat band voltage, which depends upon the metal semiconductor work function for the gate metal and the semiconductor. It depends on any trapped charges in the insulator divided by Cox. And what does Q depletion depend on? Q depletion depends on Q NaXD. Sorry, it is a very crowded slide here. So, Q depletion depends on Q, okay, let me just mark it somewhere else. It depends on Q Na into XD, okay, and what is Na? Na is nothing but your dopant ion concentration in your P type or N type doped body of the MOSFET, and XD is the depletion width, which in turn depends on the surface potential and which should be 2 phi f at the time of turn on of the MOSFET, and 2 phi f again depends on the dopant concentration. So, here is a complete breakdown of the output impedance of the MOSFET in linear mode with respect to all the device physics that we have learned so far. So, this connection is the value or the message of all these lectures. Okay. So, it is the value of talking about circuits, so that you understand not only how to design the circuit or what the circuit, the implication of the circuit design is in terms of circuit performance, okay, but also what to do and where these parameters came from, so that it helps you debug at a very fine level. Of course, this is a very, it is an introductory course in some sense, but nevertheless it has got a lot of valuable messages in this, in its content. Okay. So, now let us move on. We have answered this question, which is what is the resistance of the switch. So, we know that we are going to use the MOSFET as a switch, and we know that it has got a resistance of 1 by mu Cox W over L into VGS minus VT. Now, here is the next question. So, suppose we use this MOSFET as a switch in a switch capacitor circuit, which is a switch in series with a capacitor, and let us say the MOSFET is on. So, the MOSFET is on, and the small signal circuit or the equivalent small signal circuit can be written as replacing this MOSFET with a small signal resistor, and here is the capacitor. So, what is the time constant of the switch capacitor circuit? What is the RC time constant of the switch capacitor circuit? So, what do you mean by RC time constant? Okay. So, if people are not, I hope all of you are familiar with RC circuits, but just in case you have forgotten what RC circuits are, what an RC circuit is, let us just go down that track for in a minute. So, let us say you have a series resistor and a capacitor circuit. You have a capacitor, it is connected in series to the resistor, okay, and let us say you have an input voltage here which is appearing as a step. So, you have a voltage versus time, and it is a step input voltage. It goes from 0 volts to say some voltage V naught, and the question is what happens to the voltage on the capacitor. So, at time t equal to 0, the capacitor had a voltage of 0, but as t greater than 0, what is the voltage on the capacitor? So, that is the question we want to answer. Okay, how do we solve this? So, since the current through the resistor and the current through the capacitor should be the same, we say that the current through the resistor is the moment this is turned on at this point just after turn on. So, let us say at t equal to 0 plus, the current through the resistor is V naught minus Vc, which is the voltage drop across the resistor, divided by R, and the current through the capacitor is C dVc by dt, okay, which is basically the dq by dt through the capacitor. And solving this differential equation, you will see that your Vc is, and you apply this boundary condition of t equal to 0, Vc is 0, you will find that Vc is equal to V naught into 1 minus e to the power minus t by Rc. You will end up with this answer. This Rc has the dimensions of time, right, and therefore, Rc is called as the time constant of the circuit. So, what does the time constant mean? So, technically when t is equal to Rc, the voltage in the capacitor is V naught into 1 minus e to the power minus 1, okay. But I mean that is only the accurate quantitative definition, but essentially the time constant is a useful parameter that gives you an estimate, okay, it is an estimate or a measure of the charging time of the circuit, you know. If you want to compare two RC circuits, okay, you compare two RC circuits and you say that this one has got a smaller time constant than that one, which means to say that this circuit will charge faster as compared to circuit 2, okay, which means to say that circuit 1 is faster compared to circuit 2. So, time constant is a good measure. It is not the total time taken to charge the capacitor, okay. The total time taken to charge the capacitor is the time taken to bring Vc to equal to V naught, and that is technically infinite. You need infinite time to charge the capacitor, okay. That is not, so RC, the time constant is not the total time taken to measure charge the capacitor, it is just a measure or an estimate of the delay or the time taken during charging. Is the capacitor charging fast or slow compared to another capacitor? That is the answer it gives you, okay. So, we need to find the RC time constant. What is the time constant of the switch capacitor circuit with the MOSFET? So, that is the purpose of this slide. So, now after this discussion the answer is quite simple. It is simply the output impedance of the MOSFET multiplied by the capacitance, and that gives you a good enough answer. So, if you have a MOSFET operating in linear mode operation and somebody asks you as to what is the small signal capacitance, small signal time constant of the MOSFET, it is simply Rho in linear into the capacitance of the capacitor. So, it is an approximate model, and what is the approximation? We have linearized the MOSFET. Now, if somebody asks you as to what is the exact charging dynamics, okay, so do not linearize it. How do we go about it? We simply equate the current through the MOSFET into the current in the capacitor, which is we have taken into account the non-linearities of the MOSFET. So, let us say that is the Vc, that is the input. So, what is the current through the MOSFET? It is going to be mu Cox W over L into VGS, which is Vg minus Vc minus Vt, minus Vds, which is Vn minus Vc by 2 into Vds, which is Vn minus Vc. This must be equal to the current through the capacitor. So, it is C dVc by dt. You solve this equation and you will end up with the exact charging dynamics, which also takes into account the non-linearities in the MOSFET. So, if the voltage is concerned, if the input voltage is all very large, if the step input is very large, this is the more appropriate equation to solve. But you will find that for most cases this is not very far, the time constant you will get in this case will not be very far from the time constant you get by simply linearizing the MOSFET and using that value, okay. So, here is a simulation and it shows you the charging of the MOSFET. So, the gate voltage goes up, the MOSFET is on, and then when the drain voltage takes up a step like response, you can see that the capacitor starts charging, and this charging time constant, although it is the simulator is using the exact model, you could easily model it using a much simpler linearized model instead of worrying about solving this differential equation. So, that is the strength of having these kind of small signal models. Of course, it is going to be very useful when we study amplifiers, etc. So, it talks about the linearization of the nonlinear device around a certain operating point. Okay. Now, here is another useful circuit, but although this really does not connect us to our device physics, nevertheless it is a useful circuit for all of you to know, okay, which is basically you have a capacitor that is charged with some charge Q1, and you have another capacitor say C2 which does not have any charge on it, and you use a MOSFET or any switch for the matter. Okay. So, although we are talking about MOSFETs as a switch, you could use a MOSFET, but it really does not matter. You use a switch of any kind, okay, and you close the switch. The question is, what is the charge on the capacitor C2, okay, what is QC2 at time t equal to infinite, and what is QC1 when t is equal to infinite. We already know that Q on C1 when t equal to 0 is Q1. Okay. So, I think in this diagram I have used let us just use the variables I have used here, which is at time t equal to 0 C1 has a charge of Q initial 1, Q1 initial, and at time t equal to 0 C2 has a charge of Q 2 initial which is 0. At time t equal to infinite, C1 will have a charge of Q1 final, and at time t equal to infinite C2 will have a charge of Q2 final. And what has happened here is that the switch has been closed. The question is, what is the charge on the capacitors at time t equal to infinite? So, how do we go about solving this? So, we simply use charge conservation, right. So, if you use charge conservation, what is the total charge? So, the total charge is Q1 initial, that was the entire charge in the system, because Q2 initial was 0. So, this is simply, so this is nothing but 0, and that must equal the final charge in the system. So, what is charge conservation? So, suppose you have 10 electrons and you had to take 3 electrons away and keep them here. How many electrons do you have left here? The answer is 7. And how did we get that number? Because charge was conserved. So, you took 3 away and you have 7, and you had 10 in the beginning, and therefore, you have 7 remaining. So, according to charge conservation, you get one equation which is basically this, and after at t equal to infinite, after you have short circuited this at t equal to infinite, these 2 points must have the same voltage. Okay. They cannot have different voltages, they are short circuited, and at t equal to infinite they must have the same voltage. So, therefore, the voltage on C1 at t equal to infinite is Q1 final by C1 and must equal the voltage on C2 at t equal to infinite, which is Q2 final by C2. And using these two relations, we can identify what Q1 final and Q2 final are. So, we will leave that to you as an exercise. But here is another interesting detour. Okay. So, let us say we said charge conservation is what we need to use here. So, let us say we use energy conservation. Okay. So, what is the initial energy in the system? So, it is Q1 initial square by 2 C1. What is the final energy in the system? It is Q1 final whole square by 2 C1 plus Q2 final whole square by 2 C2. Now, is it okay for me to equate the initial energy in the system to the final energy in the system? Can we say charge energy conservation, energy is conserved, and therefore, the initial energy in the system is equal to the final energy in the system? If we define the final energy in the system in this manner, the answer is this equation will not hold. Okay. And why will it not hold? Because what we have ignored to consider here is any loss due to Joule heating in the resistor that we used. No matter what the switch and what the resistance of the switch, there will be some amount of Joule heating. Okay. And in fact, it turns out that that heating or the energy loss becomes independent of the resistor used, okay, which is an interesting offshoot from this. So, we will look at that also in some assignment. So, therefore, these two can be equated, the initial energy of the system and this can be equated only if we consider the loss due to Joule heating in the resistor of the switch resistance. So, this equation will hold true, and if you actually solve this out you should get the same answer as you get for charge conservation. Okay. So, that is a message from this slide.